We are in this talk trying to clarify the performance of the lens sensors, in particular the collimated detectors. This is a work by the University of Maryland lens team, Sagdeev, led by Roald Sagdeev, Gadana Milik, and Daniel Usakov, and supported by myself at Goddard, and of course supported by the entire lens team because the lens instrument was led by Igor Mitrofanov at IKI. Just to orient yourself, the audience, to the construction of the lens instrument, there's an array of detectors. The one that we are going to be concentrating on in this talk are the 4 collimated detectors, the CN, TN 1 and 4. You can see this structure without the collimator, and it's the collimator itself which gives the lens a unique performance of allowing it to be able to have high spatial resolution, 10-kilometer footprint at the 50-kilometer nominal altitude of the spacecraft of LRO. So this schematic illustrates the primary processes that we are going to deal with in order to calculate the performance of the collimated detectors. You've heard, you've heard, I think, in last Tuesday by Dmitry Golovin that the galactic cosmic ray is a varying component and is very tied to the solar activity of the sun. That's why the benchmark of using the Apollo data era is important, because it gives us a unique measurement of what the process is at that current era and how the process affects the modulation of the neutrons in the regolith. What its flux is what's called the leakage flux of various energy neutrons, both the epithermal and other energies which will be emitted. More importantly, we need to also model the angular distribution of how these neutrons are emitted as a function of angle. More importantly, we model what the field of view of the collimation is, how it could be seen by the 4 collimated detectors which is embedded in the collimators. And then finally, we also model the detection process in the helium-3 detectors itself. And here's the introduction, and we had this unique opportunity of using the Apollo 17 in situ detectors to be able to probe the actual physics within the 1 meter that's probed by this measurement that's placed by the Apollo 17 satellites. And so this serves as an invaluable ground truth of the processes and the fluxes that are produced in the regolith at the Apollo 17 era itself. This is the basic paper that was used as the ground truth by Dorothy Woolen, and the probe was actually drilled into the regolith and has detectors, neutron detectors in the regolith, which allows McKinney, by using Monte Carlo processes, to actually calculate the flux of neutrons at various energies which is produced by the Apollo 17 era cosmic ray fluxes. What we did in red was to use this talk complemented by our own, I think the team's Monte Carlo calculations of the angular emission coming off the lunar regolith, and calculation of the field of view of the collimated detectors and the physics of the detection in the helium-3 detectors. And then because, as you heard in last Tuesday's talk, we are in this beginning of the LRO mission in 2009, 2010, a unique phase of the solar cycle in which we have a very, very quiet sun. That means that the galactic cosmic ray itself was at the all-time high in the space area. So we have to correct this process for the current LRO error. So that's how we're going to do this calculation. We use the Monte Carlo benchmark by McKinney that uses the LPNE Apollo 17 in situ neutron production. You will see that on the left-hand side, this is flux of neutrons as a function of energy. What happens when because this is in the Apollo 17 site, is a low latitude dry regolith, so it acts as a very great benchmark. When you have hydrogen, what happens is the flux varies as a strong function in the epithermal region, and that's why we are able to use the epithermal neutron flux as a surrogate for hydrogen, potentially water in the regolith. What we did was to actually interpolate the McKinney distribution by a piecemeal series of various straight lines on this, and this is what we use actually in our calculations because we could get an analytic form of it for a numerical integration later on. We changed the scale also to EVs, and so we'll be integrating the epithermal neutron from about 0.4 EVs to about the 1 MeV. In addition, we also look at the line of sight going through the collimator geometry. This is a cross-section of the collimators itself, where the placement of the detectors, the helium-3 detectors. The collimator is a composition of boron-10 and polyethylene, and we also look at the various line of sights going through the collimators, how it intersects the detectors itself, and the amount of actual cross-section with the detectors. What is also important is the angular distribution, as seen from the ground, of the emergent neutrons. So this red is the actual portion that is seen by the collimator detectors. It's only 2.5%. And this, we've done this by just a numerical calculation, interpolating that the Monte Carlo angular distribution by an analytic expression, and integrating only to about the field of view that's given by the collimator into the detectors itself, and that gives you that 2.6% of the full neutron flux that's emerging from the surface. So here again, in summary, is what we've done in actually trying to see what the detectors see as a portion of the emergent flux itself. The next what we did was actually model the processes in the detectors. What is needed is the cross-section of helium-3 efficiency of detecting neutrons. Is given by this. You can see is also energy dependent. Also, it's in a length of 5 centimeters, the 20 atmospheres of helium-3 that's in the detectors. This is that McKinney distribution, as you remember, is a function also of energy, and we integrate this. Putting it all together with some factors due to the area of the 4 detectors itself, spherical moon, integrating underneath the detection efficiency of the helium-3 detectors, we get 1 count per second, but this is benchmarked to the Apollo 17 epoch. So the galactic cosmic ray is actually could be parameterized by this modulation potential, and the modulation potential can be estimated using sunspot as a surrogate. And so for the LRO epoch, the 2009-2010, we believe the estimate for the solar modulation potential is between 200 and 250. Already the solar activity, current era, you can see that solar modulation potential has increased. This is the Apollo 17 epoch solar modulation potential. And if you look at the various ranges, you get a factor 1.5 to 1.6 augmentation to that 1 count per second. But we're going to use conservatively this 1.5. And our conclusion is at the 50-kilometer orbit for LRO, beginning of the mission 2009 and 2010, a conservative estimate of the counts going through the 4 collimator is 1.5 counts per second. And this is consistent with the numbers that was given in Science by Mitrofanov and Allier in that Science article. Thank you.
Thank you, Gordon. Are there any questions? No questions. Oh, we have one.
We have to project back and maybe able to answer some questions.
Scan. We push him so hard, that's why he's been a little late getting more new things up, because we've been switching him so fast. Go ahead.
So there's a lot of modeling that you've done here, but when you actually look at the lend data themselves, the omnidirectional detector and the map of the moon produced by the omnidirectional detector is completely qualitatively different from that from the collimated detectors. I don't think it's consistent that you can have so much of the flux coming from through the collimated detectors. They're coming through the walls in order that you can get such a different qualitative picture from the omnidirectional and collimated detectors.
We made a very detailed understanding of what the background contributions for the lens instrument might be. And I think some of your results may be due to the way you may be normalizing the turn-ons and turn-offs of the data from the raw data. You should use the lens-derived data, which has been normalized by the team using very detailed methods. But from our understanding of the amount of flux coming through the collimator, the high energy component that you're talking about, it's about 0.6 counts per second out of the 5 counts per second we have. This is just due to the galactic cosmic ray onto the LRO structure itself and charged particles. This is the number that we just gave you, the 1.5 counts per second. There is lunar backscatter. There is backscatter coming from the back end of the lens instrument, which is very lightly unshielded. And this is the component you're talking about.
Okay. Anything else? No? All right. Thank